Good afternoon. Assalamualaikum everyone. Okay, so today we will proceed to our lecture, still in chapter 1. In last class we stopped until here. Any question from the previous class? Basically, this is the flow. Okay, so now we proceed to step in product or process design. There are 4 steps. Okay, there are 4 steps. See, I put picture of teh tarik making. Okay, so we will use example of teh tarik production for this 4 part. Okay, to make teh tarik, what do you need as your raw material? Sugar, teh, of course. Then what else? Tarik teh. One method later, process. Raw material, sugar, teh, water. Then condensed sugar. Condensed milk. This is your raw material, right? Any other additive? Sugar, you can use any type of sugar. Okay, so that is your raw material. Now, how is the process to make teh tarik? What? Stir. Before you stir, mix all together, or step by step. Take the tea, take the sugar, put in the mug or cup lah, right? Then mix. Okay, after mix, tarik. Okay, that is one of the process. International student, do you understand what we are discussing? Tarik, pull lah, pull. Okay, tarik. Do you know teh tarik? No, right? Okay. Okay, let me know if you do understand, international student. Okay, then tarik. That is part of the method. Then what is your product? Teh tarik lah, of course, right? Full of bubble. Bubble, sometimes the height of the bubble, it depends how high the person tarik, right? And how concentrate your teh. Okay. Now, from the beginning just now, it covers up to part 1 and part 2, where you identify your raw material, find suitable chemicals, process creation, how you want to do it, mix, stir, perhaps at certain temperature. Okay, then process creation. From raw material, mix, stir, tarik, that is the process creation up to your product. Okay, development base case, the basic process of all things. Okay, so once you identify the development of base case, the basic thing, raw material, put in mixer, stir, then you get your product. Okay. Now, part 2 is the detailed process synthesis, the detailed one. During your raw material mixing, how much is your raw material? How much sugar that you want to use? What type of sugar? What is the size of sugar? Tea. What type of tea? leaf tea, powder tea, bag tea, any brand that can affect your quality. Okay, water. Do you need distilled water, tap water, RO water, mineral water? Okay, so you need to identify the detailed one. Then during the mixing process, how long that you need to mix? How fast that you need to mix? Okay, the mixer rate. And then whether you need 2 mixer or 1 mixer. Okay, that is a detailed process. Is there any heat temperature involved? Do you need to heat it? If you need, at what temperature? Okay. Okay. Then for the mixer, how is the size of the mixer? What is the material of the mixer? Do you need to cover it? Okay. Do you need to jacket it for adiabatic? Okay. Then that is the detailed processing considered. For the part 3, detailed design and optimization. Detailed design. Now comes the design for your mixer. How big is your mixer? What is the height? Do you need any additional skirting? Okay, for teh tarik, of course, no lah. Do you need anything to support your mixers? Okay, then optimize. During the heating, let's say you involve heating, so that temperature, can you capture the heat transfer to another unit segment, unit op, optimize it, okay, optimize the energy. Okay, for part 4, plant-wide controllability is the control instrumentation part where you need to control your process. Okay, but if it involves temperature, so you need to have temperature controller. What happened? Analyze what happened when the temperature goes high. What happened when the temperature goes low? You must have your cut off. What is your cut off temperature? Okay, that one is the whole concept of using the teh tarik example. Okay, so that you can grab the concept first before I go into chemical process plant. Okay. Now this is the detailed one. Okay. Okay, part 1, up to process creation, development of base case. Okay, the basic flow chart, basic one. Then it comes to the details, up to part 2. Okay, so part 3, the equipment sizing, optimization. Part 4 is the control. Like your PDP, we have PDP 1 up to heat integration, right? PDP 2 from equipment sizing up to control. Then safety, economic analysis. So this course covers the whole thing. This step covers the whole thing. Okay. Now we use VCM manufacture, vinyl chloride monomer, as example. It already has a typical design problem. Okay, that means the VCM plant already operating. Okay, but then they have an opportunity they heard opportunity has arisen to new demand for VCM. Order of 800 million pounds per year. Okay, but existing plant only produce 1 million pounds per year. The existing plant. They want to increase up to 800 million pounds per year. Okay, since VCM is extremely toxic substance, it is recommended that all new facilities are designed carefully to satisfy the governmental health and safety regulation. So current plant already operating produce 1 million. They want to increase the production to 800 million. So what they need to do? They need to design new facilities. Perhaps add more reactor, add more distillation column. Okay, so this one we call as retrofitting. Retrofitting, the term retrofitting. We add in something new into existing plant. Okay. Now the process design begin with primitive design problem. Need to identify what are the problem if they want to increase to 800 million pounds production. Usually it will be examined by a small design team. Okay, a design team will be assigned to do this. Then they will try to generate more specific problem. Okay, for example, here, the first problem that might occur, the raw materials. Whether it is available in-house, that means the current plant, do they have that much of raw material to produce 800 million pound product? Or do they need to purchase new one? Or do they need to manufacture it? Okay, so these three things need to be considered. Which one is the best solution? If they need to manufacture, perhaps they need new plant to manufacture the raw material. Okay, then they need to compare manufacturing the new raw materials and purchase the new material. Which one is more cost effective? Okay. Second problem, scale of the process. Now they only have available for 100 million, right now, or 1 million, or 1 million, 1 million product. So they need to scale up the unit up so that it can produce 800 million product. Okay, like for in your lab, you do lab scale. You optimize the condition in the lab scale. Let's say you use 5-liter bioreactor, for example, 5-liter reactor. So to scale up into industrial scale, it depends on how big is your plant. So that 5-liter optimized condition for 5-liter need to scale up to, let's say, 100 liter. So everything need to scale up. Okay, then location of the plant. Should it be at the same location or you need to have new location or expand the current location? Okay. So those engineers will need to brainstorm to solve the issue. Did I turn on the mic not just now? Okay. Okay, next we go to the alternatives of the problem. Alternatives to achieve production of 800 million. Okay, there are a few alternatives over here. Competitors' plant produce 200 million pounds per year of VCM, located 100 miles away. Okay, might be expanded to produce the required amount, which would be shipped. Okay, so in this case, the design team projects the purchase price and the design storage facilities. Okay, this one, the option is to expand the plant. So the design team will project the purchase price of perhaps new equipment, the land required to buy the land to expand the plant, and design the storage facilities. Okay, next alternative, company produces HCl as a byproduct in large quantities. Okay, thus HCl is normally available at low price. Reactions of HCl with acetylene or ethylene and oxygen could produce dichloroethane, an intermediate that can be cracked to produce vinyl chloride. Your main product is VCM. Okay, the company produces HCl as the byproduct in large quantities. If they sell the HCl, it will be at low price. Current market for HCl is at low price. Okay, so they can consider to react the byproduct with acetylene or oxygen or ethylene to produce VCM. Okay, two options over here. Whether they can sell the HCl but at low price, or they use the HCl to react with other chemicals to produce the product. Okay, the third alternative, purchase and ship by pipeline from a nearby plant. Chlorine from the electrolysis of an ACl solution. Okay, this one they purchase chlorine from nearby plant for electrolysis of an ACl solution. Okay, then react the chlorine with ethylene to produce the monomer and HCl as the byproduct. Okay, you might be confused a bit. I'll share back to you the plan. If you still remember, this is the process. The VCM, vinyl chloride. The raw material is Cl2 and ethylene, C2H4. Okay, this is what it meant just now. HCl is the byproduct. The second alternative just now is either to sell the HCl or to react this HCl with another chemical to produce the same product. Okay, the third alternative, chlorine, which is required for the raw material, purchased from the nearby plant. Okay, the chlorine is required for the raw material. Then react this with another chemical to produce VCM. Okay, the alternative just now, it focused on the byproduct and the raw material over here. Another one is expanding the plant. Okay. Sorry? Yes. To buy chlorine from nearby plant. Raw material, yes. Third one is the raw material. Okay, this one expand the plant. So the engineers would project the costing and the design. Okay, this one is usage of the byproduct. This one, purchase the raw material. Which is the chlorine. Minimally to have 3 alternatives. You can have more. What is the theme for this semester for PDP? Huh? Urea synthesis. Using green ammonia. Okay, green ammonia, does it mean green ammonia or green technology to get ammonia? Green technology to get ammonia. Okay. It's two different things. Green ammonia, perhaps that ammonia comes from the waste or biomass or sustainable raw material. Green technology, the process that involved to produce ammonia is green. Safe process, green process. Okay, so for ammonia, what is the raw material to produce ammonia? Nitrogen and hydrogen. Okay, we know nitrogen, hydrogen. So how to get these two? Nitrogen you can get from the air. Involve some process. Hydrogen. How to get hydrogen? Electrolysis, green technology. But
thinking about it, it does exist in thinking you use too much water, it's not sustainable.
the water, can the water be recycled?
Because it uses what ammonia, what sort of ammonia is not such nice. That's just one. And that's carbon capture. Yeah, I guess the next right? So we should just be carbon capture from and use the carbon for our because then the hydrogen is sending production. But that's what I said. It depends on your understanding of what it is.
Yes. It depends on how you justify your process is green. Okay, so from that particular part, you can have few alternatives, right, to get your raw material. So that is the first part of design project, design process, first part. Use what? What?
Blue green hydrogen is the same mixes, blue hydrogen will produce, green hydrogen by declination, there's no carbon involved. Blue hydrogen, there is carbon involved, and carbon is reused in some way.
Reuse.
Yeah, but still, I feel like it's
Yeah, if that the case, if that how you justify green, then should be okay. Okay, so understand the alternative. This is the first part only to design your product, a process plan for your product. Okay. Now this is to find the alternatives to produce a larger amount of product. Same concept to be used in determining your process, what type of process that you require. So you should have few alternatives. What equipment that you need to use? You should have few alternatives. Like bioreactor, what type of bioreactor that you need? Sorry, not bioreactor, reactor. Reactor. Whether it is isothermal, adiabatic, or what type. Okay, it depends to your process. Now, these are few reference that they usually use to refer in designing a process plan. Okay, this one just for your knowledge now. Now, after you develop the base case, the basic part one, you create a process flow sheet. How is your process? Reaction, then filtration, then get your product, something like that lah. Okay. After that, go for process integration. Which part that you can integrate in order to optimize it. Okay, then after that, create a detailed database. What are the database that you require? Okay, pilot plant testing, modify the flow sheet, prepare a simulation model. Unisyn or ANSYS, Fluent ANSYS, any suitable software. Okay. Then after that, once you come up with the base case, then only you go for detailed process synthesis. Identify your process, whether it should be continuous or batch. Okay, if continuous, why? What is the advantage? What is the reason behind it? If higher yield, what if you use batch? What? Easier to control. So you must have advantage and disadvantages for each method. Then only you decide. Okay, because certain reaction, it requires batch process better than continuous. So if your process is continuous, what is the reactor networks? How is the separation synthesis? Okay, how is the heat exchanger network? Therefore, if you choose batch, so how is the sequencing and scheduling of the processing steps? For example, batch process. For example, fermentation process. It requires a batch process because you need to ferment it at a certain duration. Then only you recover the product, right? Okay, again for part 3, the detailed design. How is the design of your equipment? equipment sizing, the design. Where, for example, heat exchanger. What type of heat exchanger? If you say shell and tube, how many tube involved in your heat exchanger? Okay, and how is the flow? Whether it go upwards or downward, or how? For counter current, co-current. Then part 4, it should be the control part. Okay. So that's all for part 1, 2, and 3. After you optimize everything, then only you can start up the final construction, Once you get the optimization and you have the final design, then you can start the construction. Okay, so after that, you also need to consider the environmental protection and the safety consideration. Environmental protection, what standard that you are following? Standard A, standard B. If you release flue gas, what is the standard from, what is the air standard that can be released in Malaysia? Okay, we have DOE have the infos. Then safety consideration. How safe is your plant? How do you make sure the staff, the worker, the laborer is safe? Okay, what is the precautions that you need to take? Hazard analysis, yes. Hazard is the common one. They have a few more. High rack. High rack, you know. Okay, before we go to this, any question from here? The step, yes. You should be able to explain each of the steps, each of the part. For example, let's say I give you, just now we use VCM manufacturing, right? So using the VCM manufacturing, describe what is the step in part 1. Perhaps what involved in process creation? What involved in development of base case? Okay. Can student at the back? Any question? Student at the back, feel free to discuss as well. Okay, now we move to the major environmental issues in design. This is part of it. Sometimes you will see a lot more. Okay, handling of toxic waste. Now we focus on the waste stream. How is the toxicity of your waste? Okay, and how you handle it. For example, the VCM just now. What is the waste? The VCM process just now. I also don't remember. Let's see the flow, the process flow diagram. Okay. What is the waste over here? What is the waste? Can you identify the waste? This is the main product. HCl is the byproduct. We don't consider that as waste. Okay, byproduct is not a waste. Okay, waste perhaps here in pyrolysis furnace. Charcoal. Perhaps here you have some syngas. Unreacted hydrocarbons. Okay, here you see here is direct chlorination reactor. Impurities, some impurities over here. Okay, we just focus on this furnace. Toxic waste. So perhaps here you should identify what is the toxic waste produced in this furnace, from this furnace. So how to handle it? Okay, for example, charcoal, biochar. How do you handle the char? Okay. Then, come again? Yes. There are specific syngas that requires from pyrolysis. Okay, wait, I copy this process flow to the next slide, easier to discuss. Okay, just now done about toxic waste. Now, reaction pathways to reduce byproduct toxicity. Reaction pathways. So in your reaction, it might involve several pathways. So how do you monitor that reaction pathway in order to reduce the byproduct toxicity? Okay. Now, reducing and reusing waste. You must always consider to reuse or recycle your waste. Reuse, reduce, recycle your waste. Okay, in later on your process flow synthesis in your PDP1, try to consider recycle stream. Okay, usually the group that I evaluated, I will always ask, is there any recycle stream that you can consider? Most of the time, if you have water as your waste, okay, whether to recycle the water or if you don't recycle, what is the reason that you don't recycle the water? There was one group, they release a lot of water as their waste, but they do not recycle. The justification is because their recycle is not pure. They require highly pure water into their process plant. So that's why they do not recycle. But again, you can treat the water. to get higher purity of water. But then you will need to consider the water treatment plant, whether it is feasible to build a water treatment plant just to recycle the water. Okay, can understand? So costing effect also take place over there. You need to consider everything. The reason last time the costing issue, because waste water treatment, then you need another equipment for it, another labor cost for it, another control system for it. So according to their justification, they just release the water due to the costing issue. Since the water can meet the standard, so they just release the water. Okay, next one is avoiding non-routine event. Reduce the likelihood of accidents or spill. Okay, through the reduction of transient phenomena or relying on operation at nominal steady state. Okay, so here with reliable controllers and fault detection system. So here the control system is important to identify any fault process, any defect in your process, any issue in your process. Okay. Then design objectives, constraint and optimization. Design objective, constraint and optimization. Okay, this one most likely is similar to your PED. You have taken PED?
Yeah.
Huh? Taking. So you have the design constraint and everything, right? For the design. So you should consider that one as well. Any questions so far? Yes. Wait, I cannot hear you. Okay, the question from your friend just now, for the waste recycle stream, do you need to identify during the PFD or PNID? That's your question, right? Okay, so the waste you can identify from the PFD itself. Once you try to sketch out the process, what are the process involved in your process? So from there you can have your input and output. What is your product? From each process, what is your product that you are producing? So from there you can see what is the waste you are producing from the flowchart already. PNID is after you settle with your PFD. You confirm on everything, all streams, then only you move to PNID. Okay. Okay, any other question? Student at the back. Any question? Any question? Okay, this one from here, this one is before the control system, before you install the control system. Okay, so from here you can already identify where is your waste already. Okay, you can identify what type of waste that you are producing. Few examples of a disaster that had happened few years ago. Okay, so this one, disaster on 50 tons of cyclohexane released from a plant. Okay, leading to release of vapor cloud and it detonates. Okay, so the impact, total loss of the plant and death of 28 plant personnel. Okay, from here you can see how big is the impact toward the environment and also toward the human. So that's why you really need to check your process flow specifically. Identify is there any problem? What type of control instrument that you need to install in order to avoid this kind of issue. Okay, the cause over here, discharge caused by failure of temporary pipe install to replace cracked reactor. Okay, the reactor crack, then they install temporary pipe. The temporary pipe fail. Okay, so it cause explosion because the pipe cannot sustain the condition. 10 bar and 150 degrees C. The 10 bar, the pressure. It cannot maintain that 10 bar, it cannot sustain that 10 bar pressure, so it explodes. Okay, here. Safety issue as well. So here, the pipe. The temporary pipe is also important, even though it is temporary. Because it needs to meet the condition of the process as well. The properties should be the same as the reactor so that it can sustain the condition. Okay. Now, these are the lessons that you can learn from this disaster to develop processes with low inventory, especially of flashing fluid. Okay, so before modifying the process, carry out a systematic search for possible cause of problem, then construct modification to the same standard. Okay, the standard should be the same, even though for temporary equipment. Use blast-resistant control rooms. Okay, what does it mean by blast-resistant control rooms? resist to the blast. So even though an explosion occur, the control room still there. Okay. Control room, they have the screen to monitor. So usually technician, engineer will be in that control room. Then carry out the hazard analysis. Okay, safety. Now this is the sample of hazard analysis. In your PDP, I can see from previous one lah, certain groups, they just simply put the hazard analysis. Sometimes just copy and paste from CNN. Okay? You need to understand what you are doing, because if the examiner is Miss Suhana, she will really dig on the safety part. So for example, this one. Study note is the valve. Okay, possible causes. This is the possible causes, possible consequences. Then you need to identify what are the action required. Each of these, let's say here, install flow meter and low flow alarm to alert operator. Why do you consider to install this flow meter and low flow alarm? Okay, you must know the reason behind each of the proposed action. Replace or clean the valve. Okay, why do you need to do this? Clean with what? Replace with what? Place controller on critical instrumentation list. What do you mean by critical instrumentation list? Okay, you should be able to answer those questions. Okay, next example is the Bhopal. This one is famous one. 1984. Water leakage into MIC storage tank. Water leakage. Leading to boiling and releasing of 25 tons of toxic MIC vapor. Killing, okay, this big number of civilians and injuring tens of thousands more. Okay, so the disaster area is very large, the disaster area. The cause, MIC vapor release because the refrigeration system had been shut down. Okay, refrigerator system had been shut down. So scrubber was not immediately available. Flare was not in operation. Okay, so as engineer, that is why it is important every morning you will need to do the you will need to walk around inside the plant to do the checklist. So those who had experience during co-op in manufacturing or process plant, you need to do the checklist every morning. Right or not? Last time in my intern in Time Tire, Continental, under maintenance department. So every morning I will walk around the plant, the factory, to do the monitoring, the checklist. Everything should be in order. Okay. Now the lesson learned over here, avoid using hazardous materials. minimize stocks of hazardous material. Okay, again, carry out the hazard. Train operators not to ignore unusual reading. Okay, this one not only for the operators. Engineers should know as well. What do you understand of unusual reading? Error. Error. Error is error. But unusual reading? Not a desired condition. Okay, so let's say your optimum temperature is 100. High level should be 120. Low level is 80. Okay, usually your process maintained at 100. Suddenly one day you saw your process goes up to 110, but not yet reaching the upper level. So what you should do? Do you just say still in the range, so don't have to do anything? Huh? Can what? Cannot hear you. Again. Recalibrate. Recalibrate the equipment. That one of the options. So that is what it means by unusual reading. Not the reading that is not the similar as when your process is running. Okay, unusual. Even though it's still in the range, but it is unusual. You need to go to the equipment and check what happened. Don't wait until it reaches 120. If it reaches the higher level, you have lesser time to maintain the thing, to control the thing before it explodes. Okay. Now, next one, keep protective equipment in order. Control building near major hazard. Okay, the third one is the Challenger, the space shuttle, 1986. Okay, it exploded just 70 seconds after the lift-off. All astronauts dead. Is dead. They were dead. Astronaut, you know, it's not easy to get astronaut. Okay, right. So the cause, because of the O-ring problem, was known several months before the disaster. Okay, they already know, but downplayed by the management who overrode the concern. Okay, that's why sometimes it always an issue between the engineer and the management, because the management didn't understand the engineering part. That's why we as engineer really need to explain to them so that they understand the importance behind it. If your own company, you can fire it. Okay, so the lesson learned, design for safety, prevent management override. Certain management, they don't bother on the maintenance thing, and they are not willing to support on maintenance because they say it didn't bring any profit to them. Okay, then of course carry out a hazard analysis. Okay, so these are the design for safety. Can read through. Okay, this one you can read through. Okay, we will go into new subtopic. Before we start, we just take 5 minutes break. Okay.
Thanks.